Welcome to another RDWorks Learning Lab. I'm going to be tackling today, and maybe for the next few sessions, a subject which really, I suppose, hasn't interested me too much because I've been so interested in the technicalities of the machine. But of course, a lot of you guys out there, apart from using these as a hobby machine, you're running small businesses with them, and you have to do the job professionally and cleanly. Now, I get all sorts of questions asked of me about various cutting parameters, and I have to say, this is a personal opinion, all the cutting parameters that I've seen out there are basically meaningless. I chose my words carefully there because I was going to be a little bit rude. I'm going to be looking at the subject of parameters and devising the best parameters for your machine, because to be honest, there's only one set of parameters for your machine, and they're the ones that you devise. Who knows what lens you've got in? Who knows what your air assist is? Who knows what power you've got actually coming through your nozzle? Who knows what power you're developing at your 50, 40, 60 watt tube? They're all unknowns. So nobody can actually give you a set of parameters that will work. They might be able to point you in the general direction. There's all sorts of materials out there, and every one of those materials requires its own set of parameters, but it requires its own set of parameters for your machine, not the vendor's machine, where these parameters were generally developed to try and give you the impression that they're being helpful. They're just being misleading. I'm going to justify myself in the way that I always do, demonstrating to you why I'm fairly vocal about this issue. I've got my little red book here, which is quite a thick book, and previously it was full of my girlfriend's addresses, but since I've been married, I've had to repurpose it. Anyway, now it's full of boring information, cutting parameters. Now, this is not a sheet, this is not a book of cutting parameters. Let me just explain. This first sheet here is cutting. This second sheet here is marking, in other words, outlining or using the laser to draw with. You require a completely different set of parameters, and whoever has told you, where have you ever seen a set of parameters for marking your materials? The third one is for dot mode. Dot mode is a very powerful technique which we shall get onto eventually. We now move on to engraving. Engraving, one word, but many facets. First of all, we've got continuous engraving, the sort of engraving that you get when you generate characters, for example, within RDWorks, text. You zip backwards and forwards and you continuously engrave the text in a scan mode. That's one type of engraving. Another type of engraving is with bitmaps. Now bitmaps break down even further because we've got straightforward black and white bitmaps like logos. The problem with a bitmap is it's made up of dots, and so you have to treat bitmaps, whether they're black and white bitmaps, which actually I don't think you'll find that these black and white bitmaps are quite what they seem, because RDWorks seems to mess with your bitmaps, and they're no longer black and white, but they're black, white and two shades of grey. So another problem. Here we've got bitmaps dithered, the same sort of thing that you get with like newspaper photos. Yet another type of requirement for parameters. Then we've got bitmaps which are grayscale bitmaps, continuous variation, which these machines can do. So, I mean, look, we've got about, what, 6 or 7 different types of parameters there. If you go about understanding what your parameters are all about, and you work to some of these sheets that I'm going to be talking about, using methods that I'm going to be telling you of, you will gain a much greater understanding of your machine and the individual parts of the process. Now, it's a bit like, probably you may remember your mum baking cakes. She'd go to the cupboard, take ingredients out, chuck them in a bowl, no scales, put them in the oven, no timing, just twiddle the knobs, and every time you'd enjoy a fantastic cake. She understood what each one of those ingredients did to make up the whole. And that's what I'm going to be hopefully trying to give you here. The knowledge of all the piece parts so that you can put them together and make a good process. Because at the end of the day, you guys are out there probably trying to sell a product. And the better quality your product, the more chance you've got of selling it. We need to first of all find out the best and fastest way to cut. And then we need to find out the cleanest way to engrave. I'm going to present to you the fact that there's a total dichotomy of requirements for those two processes. Technically, you can't mix them, even though you want to. But there are ways that you can do that once you understand what the individual elements are. So it's a huge subject, and I'm sure it's going to take probably maybe 4-5 sessions to cover not all of, but just the initial parts of this. Now, I'm going to admit to the fact that I've already done some work on this for ThinkLaser on that machine behind me. And that was when I became really aware of how remiss I've been in examining in detail or telling you how I go about working my machine. I'm more interested in the technicalities behind it rather than the technicalities of cutting and engraving. Now, I'm not an engraving expert, so some of this stuff I'm having to start from the beginning, and I'm learning as well. Cutting I've been doing for a long time, and what I'm going to do is demonstrate to you the ways that I get to my cutting parameters. And some of the factors that can be involved with cutting are quite surprising to get the best cutting. So I'm going to use that machine over there because it's got something on there that I haven't got on here, which is a honeycomb bed. Now, I'm not a lover of the honeycomb bed, but it has got its uses, and it's a great tool for demonstrating how sometimes it's not that good. I'm going to cut together bits and pieces of video that I've created already using that machine over there. And we'll go into a series of videos where hopefully you'll come out of it a much wiser person. I know that I've come out of it wiser, especially after studying some of the parameters that you need for engraving. Okay, so you've spent ages creating all this lovely data. You decide you need another machine. Maybe it's going to be an 80 watt machine as opposed to a 60 watt machine. How do these parameters work for you then? You need to be very careful because you'll be putting all this information here in something called percentage power, which is what you see on the display here. That's what this machine works in, percentage powers. It doesn't work in watts. So all the parameters that you've got in here could actually be quite meaningless if you move to another machine. So how do you overcome that problem and make your results meaningful? Well, you can't fully protect yourself, but you can protect yourself to a reasonable extent. Good advice would be to see about a power meter of some sort so that you can physically measure the power coming out of your tube to generate this calibration graph against percentage power. And then if you get another tube, you can draw the same graph and you can work out what the power differences are then between percentage power on a 60 watt tube and the same percentage power on a 40 watt tube. And you can start to adapt and modify these parameters without going through the whole process again. Over a period of time, we will gradually tackle every one of these subjects and start filling in the parameter sheets. But they're all separate subjects, all on their own, that I should be tackling during this series. The first one is cutting. Now, the word cutting is in some ways a bit of a misnomer because you're not really cutting. What you're doing is burning. All organic materials like wood, leather, paper, card, the process by which you cut them is burning. Acrylic is a unique material in that it sublimates. You fire heat at it and it evaporates. Everything else burns. Now, never lose sight of the fact that your laser beam is not an innocuous beam of light. It's a very powerful beam of fire, just over the thickness of a hair. And it can do a lot of damage, but it is fire, heat, concentrated heat energy. And it will burn, and it will char, and it will smoke. We're not going to spend too much time initially filling in this sheet. What we're trying to do is quickly get to the parameters that we can record in here as being the correct recipe. The first thing we need to do is choose a material. And we're going to start off with something nice and simple. Here I've got a piece of 1/8, 3.125 hardboard. It's a high density fibre board. So the next thing you'll need to do, I would recommend that you get yourself a program built into your machine here, which is a 40mm square or a 50mm square, something small and compact like that. So you can draw that in RDWorks and program it up with cutting parameters. It doesn't matter what the parameters are that you put in, because we're going to edit those here on the machine itself. Now, to do this cutting, we could use this table. The problem is, people think that you get good extraction through this table, but look, how much extraction am I going to get through here? The answer is very little. The way to get good extraction is actually to let it happen underneath the job like that. So what I'm going to do is to pack that job up onto little packers. Now, I've mentioned to you before things like these. These are dome nuts. Anything will do for packing up. And then on this 2-inch lens, I need to set the focus to 5mm above the surface. There we go. So we're basically set up now, but what we haven't done is set any parameters. My suggestion is always use the maximum power that you can. I'm going to set the parameters to 67%, which is the maximum I can run on this machine. And then I'm going to set a fairly slow speed. This is the guess. This is a experience. This is a finger in the air, but at least we shall find out, because if the square does not drop out, we're going too fast. And if the square does drop out, we're not going fast enough. So we can't lose whichever way we go. We've eventually got to get to the point where the square doesn't drop out. So we'll start off at something like maybe 4mm a second, very slow. The other thing that I want you to note is I have got this air assisters fully open. It's most essential for all organic materials when you're cutting them to get the most efficient airflow you can through that very thin cut that you're going to produce. That is where the smoke is going to occur, and that is where you've got to get the smoke away from. You don't want any smoke basically coming back up onto this surface. If it comes back, it will get blown down again and it will produce a brown mark around the edge of your cut. So you'll know that your efficiency of blowing is not very good. So I'll now turn the extraction on. Look how clean the cut is. As I mentioned to you, all organic materials burn, and burning produces smoke and charring on the edge. Now, one of the ways of knowing whether or not you've got a good cut, or you're getting close to the maximum that you can achieve, is to carry out this simple test. Get a piece of white kitchen towel and try rubbing it along the edge. Now, okay, we've got nothing coming off there at the moment, but that may be because this is not a pure wood. This is a man-made wood with resins in it, which will actually harden off. It looks very, very black. Looks quite nice, but it looks black, and I'm not expecting it to be that black. Now, we will see what happens as we get a little bit faster. Let's double it. Let's go to 8mm a second. We could go up in single steps and spend ages doing it, but let's double it, because the worst that's going to happen is it doesn't work, and in which case we know that the result the good result is somewhere between 4 and 8. So we go through this halving process, doubling and halving, to get to a quick result. And I think it's it's important that I keep showing you this. You can see the colour differences between 1, 2, 3 and 4. They're getting lighter and lighter and lighter as we're getting faster and faster, and the burning and charring is getting less. We can't go to 32, but we'll add another 4 and we'll go up to 20. Although there was smoke coming out underneath, indicating that it was cutting, you'll notice something else now. If we compare these last two results here, you can see the burning, the browning around the edge that's not there. So we've reached a point where the smoke is beginning to just back up a shade and come out on top. Although it's cut through, and it's cut through very nicely, we may actually have reached the limit. There's our colour comparison. The difference between this one and this one is not very different. And I think at 20 millimetres a second we've probably reached the absolute limit. We could push it to 22 and see what happens. No, it's just not falling out. I mean, it's cut through extremely cleanly on the back, but it's hanging just on these corners, because what's happening is the cut, as it travels along, is actually this shape. The beam is dragging. So when it gets to the corner, just here, there's a little bit there which is not quite cut, and then it starts coming towards us. And that's probably these little corners here which are hanging. We have reached a limit, but what we'll do, we'll go beyond the limit, 22 to 24. We could say that this is actually cut. It's done a superb job on the underneath here, and that's another trick that I will point out to you. You don't always cut a product like this face side up. It's often better to cut it from the back, because the back side is often extremely clean like this. Yeah, and that's just hanging in on the corner. Okay, now you may think that we've found the limit. So now we're going to change another variable to see whether we can have any major effect. Now, one of the most underrated variables is this thing here, airflow. Another reason why I've turned the extraction off is so that you can hear the airflow coming out of the nozzle. But when I turn it down, and I'll flip that round a minute so we can see what's going on. But when I turn it down, is it on? Is it off? Is it working? Is it not working? What's happening? You can hear it when there's lots of airflow, and you can hear it when there's no airflow, but it's that little bit in between, which is actually quite crucial. I'm going to show you a little trick that I found extremely useful. Now, here I've got a little pot of water, which I keep handy. So I can make a lot of bubbles. But what I'm trying to achieve is just 1 or 2 bubbles. And it does show you that we've still got airflow coming through there. Even when the valve is off, it's leaking. So we've got just enough air coming out of there to stop the lens from fogging up. So we've basically turned the air assist off, but left enough on to protect the lens. We're still doing 24 millimeters a second, which is this last one here. Did you notice anything? Hell of a lot of smoke. But the thing that I really want you to look at is this. Smoke, no smoke. Bit of a puzzle. You normally want maximum airflow to get a cut. We get lots of smoke coming up, but what happened to that smoke? let's look at it again and observe what's actually going on, because part of the process of getting the best parameters is using your eyes. Take a look carefully this time at what's happening to the smoke. Can you see how it's blowing up from the surface? And then what's happening is it's getting carried away by the air. Now, I've got the door open at the moment, so what I'll do, I'll close the door, because you would normally be operating this machine with the door closed. I've got a big air gap underneath the door, which means I get a very high jet of air that passes through the machine. So can you see how the smoke is actually drifting upwards? It's not being blown down and recondensed onto the surface. I mean, the edge is beautifully clean, don't get me wrong. It's done a superb job with this product. It might not do the same with wood, but with this product it's done a wonderful job without the air assist. Slower, slower, faster, 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 no air assist. That's counterintuitive to all the advice that many people will give you. It's not the same as normal wood, because this is man-made wood. So that's one major factor that we've changed, and we've seen the results. So we think we've got to our maximum speed of 24 millimeters a second. Let's see if we can improve that in any way at all. We've improved the cut, we've kept speed to a maximum, and now we're going to try something else. You may remember that this was set to 5 millimeters. I'm now going to drop this down to 4 millimeters. I did warn you that these fumes are flammable. It has only just about cut. So what we'll do, we'll go the other way and we'll lift the nozzle out 1 millimeter. So instead of 5 millimeters, we'll set it to 6 millimeters. Well, we certainly didn't get any flames that time. The product just about falls out still. So we seem to get the best results when we took the air assist off. Certainly -1 was giving us flaming, and it was only just making it through, but then again it was only just making it through on all of these, so whichever one of these we chose, it was right on the limit of cutting. So we've reached that limit at 24 millimeters a second. We've now got to look to see what other attributes we would like to get out of our cut. The cleanest edge is probably the best thing that we can go for. Now this one here at -1, although we were producing all sorts of flames, we didn't damage the surface. But I think this one here at no air assist, normal 5 millimeter optimum focus, I think the optimum focus 24 millimeter was probably the best one to go for. So we've settled on several things then for this material. 24 millimeters a second, 67% power, no air assist, on standoffs. These all look nice and crisp and clean on the surface at the top. This was the first one that we did very, very slowly. And one thing I'd like you to note on this one is how burnt the bottom edge is. Can you see how charred and brown that bottom edge is? Once we started getting a little bit faster, we get lovely clean bottom edges. So there's some other factor that tells you whether or not you're going fast enough or whether you're going too slow, and that's whether you're getting smoking on the bottom edge. Right, now is the time to start filling in some data in our book here. Now it's high density fibre, HDF, 3 millimeters, let's say it's 3.125, but 3 millimeters. Now the important thing is here, we were using a 2-inch lens. And so all the data is going to be filled in across this column here. The offset of the focal length, we tried -1, and it flamed up. We tried +1 and it was okay, but optimal was probably 0. So the offset was 0. Minimum power, well, when you're cutting, there are exceptions, but in general, minimum power and maximum power are always set the same. The reason why you'd use minimum power is for cutting is a specialised subject which I will tackle at a later date. So at the moment we had 67% and 67%. I don't know what the workface power is. We'll check that in a minute. We do know what the speed was. The optimal speed that we found was 24 millimeters a second. Now, air assist 0 to 3. We've got a code down here. 0 is off, 1 is just on, 2 is low flow, and 3 is maximum. We had 1. The work support method, let's just say that they are 12 mil. If we just put a dimension down, that will tell me that we've just lifted it 12 millimeters off the deck. Now, edge finish, very good. We can put note 1 there, for example, and down here we've got additional notes, and we can put 1, light brown, no charring. Oops, air assist was 1. Table type, what were we using? We were using the honeycomb table, so that was B. Now, one thing we've missed 2 things out. Dimensional error. I thought I'd put a 40 by 40 program in there. When I measure this, or when I'm just about to measure it, I realise, hang on, that's not 40 by 40, that's probably 25 by 25, which is another program that I've got loaded in the machine there. Knowing that this was supposed to be 25 by 25 to start with, it's finished up at 24.88, say 24.9, 24.86. So on average, it's lost 0.15 minus 0.15. Now that's a very important piece of information, because if you're trying to make pieces that fit together snugly and tightly, you need to know what the error is. Now bear in mind that this is, and I really oughtn't to put, is plus or minus. I oughtn't to put any dimension on that, so it's plus or minus, because if you're producing a shape like this, it's going to be minus, but if you're producing a hole, it's going to be plus. So technically it looks as though that cut width, the kerf, is 0.3. In other words, it leaves a 0.3 gap all the way round. One vital piece of information that's missing off here is what power we were actually using to do that work with. And the only way we can find that out is by measuring the power that comes out of that nozzle with a power meter. Here's my little power meter wand that you've seen me using before. Now it's necessary in this case to have it on a little stand, because you can't use the machine with the lid open. Now, the way that this stand is designed is such that it's got a location pin under here which sits under the centre point of this thing which I call a doohickey. Now, even if this rotates, it won't really matter, because the centre point will remain the same. They're going to move the head to a position on the centre of this target here. We've got to, because the beam is focused through the lens, if we drop that down to just 5 millimeters, which is the focal point, it will do a nice engraving job on the surface of that black aluminium. Now that's anodized aluminium, which is 100% absorptive to the rays of energy that come out of here, the heat energy. Natural aluminium is reflective, anodized aluminium is 100% absorptive. We've got to drop this down about 2 inches. So I've got pulse now at 15%, and what I can do, I can just gently pulse that, and we shall see that we've got about a 2.5 millimeter diameter. I'd like to see that at about 3 millimeters. So we'll drop the distance down a little bit further. And we'll do another pulse. And as we've got the lid open, I will do everything in one spot so that you can see what's going on. So the number that we need to remember is about 8.4. We'll start the system off to start with. I'll set the maximum now, so 8.4. So I've already put that into my calculator, 8.4. We'll just wait for the temperature to max out. 29.8, 8.4 minus 29.8 equals, don't worry about the sign, times 2 equals 42.8. 43 watts is the power that we've got to put down into our chart. There's 43 watts. And now what we've got to do is exactly the same thing again, but this time we've got to do it for a 1.5 inch lens, and then I should do the same thing for a 2.5 inch lens, and I'll also try and do the same thing for a 4 inch lens. And what you will then see is the comparative power that it takes to force each one of these lenses through that material. In other words, we may be able to get better than 24 millimeter per second out of a 1.5 inch lens on this thin material, but I suspect when we get up to 2.5 it will drop down. But it really depends on what power is coming through the actual lens itself. So again, I'm just trying to make it clear to you there are so many variables in here that only you can find out what happens correctly on your machine. Now, I'm not going to subject you to the trauma of going through each one of these lenses. I will come back to you with the results when I've done them, but basically you've seen what the procedure is and how tedious it can be. And I've put HDF here. I'm going to change that to MDF because I did a little bit of research and I think this is something called laser grade MDF, and the only reason it's called laser grade MDF is because it has a lower formaldehyde emissions content. How much lower? It's difficult to find out. But basically it's MDF. Now, as I said, I think MDF is going to perform differently to wood. So we're going to go with a little piece of wood next to see what the difference in results are. Now here we've got a piece of 10 millimeter plywood, and we're going to try, first of all, with this 2.5 inch lens. We'll work the other way around this time because we happen to have the 2.5 inch lens in. So the ideal situation would be to have 5.5 millimeter gap. We're going to start this test off somewhere in the middle. Let's just say 10 millimeters a second. We've got full power on again. We're going to turn the air assist on, and that looks like it's cutting through very cleanly because we've got no browning on the surface. We'll just check the edge, and we'll check it with the tissue, and we appear to have virtually no browning at all on it. It's a lovely clean edge. Let's go up to 14 millimeters a second. We're certainly looking fairly clean on the surface, and it hasn't cut through. So 14 millimeters is one step too far. We were doing extremely well here at 10 because we had a nice clean cut which told us that we were more or less at the right maximum speed. We could try 12. If we look closely here, you'll see that it hasn't really cut through, and it certainly hasn't done it on the corners. You can see where the corners have dragged. You can see these little bits that are missing here, look. But that's not a cut. That's a struggle. So I think we found the optimum at 10 millimeters a second. That was a bit of a lucky guess. So let's see what other factors we can change to maybe improve that 10 millimeters a second. Now we know that 12 is right on the edge of cutting. If we can make 12 cut, then we've made an improvement. So what can we do? Well, the first thing we could do, because this is a thick material, we could drop the focus point down. So let's drop it down to 4.5. So we're still running at 12. Is this going to go through because we've dropped it down by a millimetre? Well, maybe, nearly. Let's just see what we've done. Well, we've maybe improved it a bit. We've still got a hole in the corner there, and we've still got bits here that haven't cut. So we'll drop it down another millimetre and see whether or not we can get the ultimate improvement. This is 10 millimetre thick material, remember. Ideally we want to be somewhere between 1/3 and 1/2, so the book says, through the thickness of the material. We've only got a 5.5 gap, so this is 10 mil thick material. Let's go down another millimetre to 2.5. 2.5. Well, to be honest, I don't think that's had any effect at all. I think it's got worse. So we were very lucky in that we found probably the ideal cutting conditions almost at our first guess. From the front we can see the obvious difference between going low here and even lower here and going high. Here is 0, -1, -2, and this is +1. Okay, so we're just filling in for our plywood. 10 millimetre thickness, 0 offset for focus. Power was 67, workface power was 48 from what we found out with the 2.5 inch lens. 10 millimetre per second speed. Air assist was full on. We were on the honeycomb table. Work support method was 12 millimetres above the surface. Dimensional error, 24.9. Let's just check that. Average about 24.8, and this way varying, but about 24.8. So that's 2 millimetres, 0.2, 0.2. Now, we really ought to check to be sure that this dimension in here is actually 25.2, which it is. So, yes, the error is definitely 0.2. To keep a little box of these samples so that you can always go back and check what edge quality you had. The thing that we ought to put on here to be sure is just a 2.5 inch focal length lens, and this one was a 2 inch focal length lens, so we know the conditions under which we got these ideal cuts. Okay, well, we've finished up with our final set of results for plywood, which was the 1.5 inch lens, which we thought might be a little bit hopeful. It was hopeful but interesting and revealing. We found that the best results, surprisingly enough, was at 0 offset. Now, all the books and everything will tell you that I should have had that lens probably set 2-3 millimetres into the material. Same with these lenses. It appears not. Now, that may be a unique property of plywood. I can't say. Maximum power, maximum power, minimum power were the same all the time. As I said, we'll always use max power, and we'll decide on the speed that we can get for the maximum power. And here we found that we were able to get the same speed for 2 and 2.5 inch lenses. So which one would you choose? Difficult to say at the moment. With the 1.5 inch focal length lens, we were only able to go at 6mm a second, which was a little bit surprising, but then again it was a thick wood and hard work for it for such a short focal length lens. But the puzzling thing was, as I said, the fact that I had to have the lens set right on the surface to get the best penetration. Now the air assist was right up at the top, maximum, and the interesting thing here was that I was getting some really strange results in terms of the dimensional error. As you can see, the best dimensional error, the tightest dimensions, were actually on the 2.5 inch lens. And the surface was good and the finish was good. So on balance, I suppose for 10mm, I've got to say that I would probably favour the 2.5 inch lens. But I hope you're getting an idea now of the way in which I'm going to be using these charts and the way in which they point you in the right direction. It tells you which lens to use, what speed to use, whether or not you should or you shouldn't use air assist, the surface finish of your product. Everything is built into this chart. You may or may not have this chart on your desk, and so it might not be the most convenient thing in the world for you to carry around once you develop this chart. We can make life a little bit easier for you. So let's go back into the office and we'll take a look at RDWorks. So here's a shape we want to cut. So if we open up the cut parameters, somewhere on your machine you will find an RDWorks V8, which is the file that contains all the RDWorks information. Even though you load different versions on, what will happen is it'll always find this RDWorks version 8 and overwrite it with the latest version. So if we click on that and we take a look what's in here, if we get down as far as the parameters, you'll find that we've got something here called parameter manager, and that's as much as you'll find about parameters. So let's close this for a minute, and then we come back here and we'll look at the top of this parameter layer, and we find there's something called a parameter library. Now there's a really weird way to fill in the parameter library. There's a certain amount of logic to it, but you have to get your head around it. So the first thing to do is to decide what parameters you want in here for a particular material. So I've got my big red book in front of me, and we're going to be putting the parameters in to suit 3mm MDF. So we decided that the best speed was 24mm a second. Blowing, yes. Process was cut, yes. We won't worry about anything in advanced. The power, number 1, yes. 67 and 67, fine. We don't want any of this stuff down here. So as far as RDWorks is concerned, we've defined everything, speed and power. Yes, I think we know a little bit different now. So let's now go to the parameter library. What we want to do is to save these parameters. So we save as, and it will tell me what I want to save it as. Well, the title is, and bear in mind these are likely to be ordered in alphabetical order, MDF 3mm. We'll put the size last. Let's move this out the way. Let's move this out. Let's move this. Oh, so it won't let me do that. So now you've got to remember what might be in this library underneath here because you can't see it. So what I will suggest you do now is to put all the stuff that you can't put into this parameter library into your notes, like FL offset 0 equals 0. You can just do a carriage return. No, you damn well can't.
So okay, we've saved it as. So we can always get back to this parameter, 3mm MDF. Let's close this now, exit. Let's close the library and let's go back to the file manager. And now we shall find above the parameter manager, we've got something called parameter library, which has appeared. We've started creating a library. Now, if I double click on that, it will say Windows can't open this file. So you can select a program from your list of installed programs to look in this library. Depending on what version of Windows you've got, you might be able to look into it with Notepad. It's got to be a fairly advanced version of Windows. I think Notepad might not work. I think you may well have to look in WordPad. Now we're in WordPad, we've got all these things that we can look at. And here's our maximum power and our minimum power and all the stuff that we don't need. But the thing that's important to us is what's at the top here. Okay, now we can't use a carriage return. We found out what happens. But what we should be able to do is to probably put a comma in there, or even a space or a dash or something like that. Let's try a comma. And we should be able to carry on with the notes now. Air assist, which we could abbreviate once we get a feel for it as AA equals number 3, because you can always refer to that on your chart if you get lost. Now the table that we used was B, which is the honeycomb table, and what we could do is combine that so that we put B and the dimension for the standoffs 12, just to note that you've got a standoff, as opposed to leaving it on the table, which would be just B. And then you've got comma dimension, the dimensional error. And I'm going to put that in as dim equals, in this instance it was 0.15, and the most important part of everything was the lens was a 2-inch lens equals 2 inches. So we've managed to transfer all of our notes now into the library. So if we do a save on that, okay, now back in RDWorks we open up our layer parameter and we'll find all the dimensions in here. Let's change this one for example to 2. They're all rubbish parameters. So we go to our parameter library and we open up MDF 3mm. Click. We get all our information, additional notes across the bottom there, and all our information about the parameters here. So what we need to do is press load, and those will automatically get transferred back into here. Now I've put the wrong dimensions in here purposely, because what I want to do now is to show you how to edit things if you need to. So we really want those to be 67 and 67. After we've corrected the parameters, we need to select the parameter library and we need to do a save as. And we need to save it as exactly what this file name is here. But, and here is the but, if you do just this, what I'm going to do, and I'm not going to do it, if I say MDF space 3mm, where have all my notes gone? They're not there. So what you'll do, you'll wipe out the parameters that you've laboriously spent time putting into your library. So you cannot edit the library in this, what would appear to be a fairly simple and logical way. Cancel. Cancel. We've got to go back to this file again. We've got to go back to the parameter library, and you'll notice that once we've opened the parameter library with a known program, it'll continue to keep opening for us. So what we've now got to do is to find out where our problem was, and the problem was here in our max and min, and we need those edited to 67 and 67. And now we can save it. And when we open up our library now, parameter library, MDF 3mm load, all our parameters are still there, including our notes, and we can load those parameters into here, 24, 67, 67. Job done. Okay. I'm sorry that's a bit of a drag. I've had to purposely make mistakes to try and reinforce to you how this system works. It is not logical and straightforward. Well, I can assure you that once you start checking out your own materials, trying to find the parameters that best suit your machine and that material, you will find it a lot more interesting than I've been able to make it today. Now, we've only looked at one of my parameter sheets today. There are another 6 in the series which we shall laboriously trog through eventually, but I'm very happy at this stage to release all 7 to anybody that would like to use them. All I require from you is an email address, but send it via the YouTube private messaging system. Don't publish your email address on the open forum. I'll send you a Word document. Do as you wish with these documents. They're no longer my responsibility. You can modify them. You can publish them on any local forum that you wish. You can chuck them in the bin. Once those documents leave my desk, they're a bit like my kids when they left university. They're looking after themselves and they're earning very, very good money. One of these days, I expect to be looked after in a very, 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 very nice rest home when the time comes. Now, just one final comment. If you can discipline yourself to fill in these parameter sheets, you have got a basic record of your machine's performance. Not only how it performs cutting material, but the performance of the machine itself, because every time you come back to cut a material and you put those parameters in your machine and the material does not cut, you know that there's something wrong. So in a strange sort of way, these parameters are a health check for your machine. Now, I never know what the next session is going to be. It just depends what drifts by and attracts my attention. I do believe that the next session is likely to be a precursor to engraving. An interesting session, I can assure you. Thanks for now, and I'll see you next session.